In this lesson, we are going to be looking at blocking and non-blocking assignment. And this is a very important topic, not on design point of view, but also on important point of view. Okay. During interview in VLSI interview, they ask these questions and what is the difference between blocking and non-blocking assignment. And I will explain blocking and non-blocking assignment in details, okay, in this lesson. Blocking and non-blocking assignment. Blocking assignment, normal, this is a blocking assignment, okay, and this is a non-blocking assignment. This blocking assignment executes in series, okay, because a blocking assignment blocks execution of next statement until it completes. Means, let's say A equal to B and C equal to A and D equal to C. So this is a blocking assignment I have used here, okay. So it executes in series, means first this line will be executed, next this line will be executed, and next this line will be executed. So this is executed in serial fashion, okay. And why this happens or how this happens? What it does actually, this blocking assignment, it blocks assignments, the execution of next statement until it completes. Means this line won't be executed unless and until this line is evaluated first, and this third statement won't be evaluated unless and until the first and second two lines, line number 1 and 2, this is executed or evaluated. So these statements, means this blocking statement, it blocks the previous, means if the previous statements are not evaluated and have not been evaluated, then the next statements that is going to be evaluated is blocked. Means in this case, this one is blocked, the second statement is blocked unless and until the first one is executed. The third statement is blocked unless and until first and second statements are evaluated, okay. So, and that's why it is called blocking assignment, because it is blocking the execution of the next statement until the previous one is completed, okay. So this blocking comes from this concept, okay. And why this thing happen? Because for example, here C equal to A, and from where this A value the C will get? From the previous statement. And how the D value will be updated? From the C, and from the C, this line, second line, from the second line. So unless and until the previous line is executed, how third line, or how the second line will get the data. For example, if you consider the third line here, the third statement, D equal to C, if the second line is not evaluated yet, then how the D value will be updated by the C value, okay. So that is one of the reason why blocking assignments blocks the execution of next statement unless and until the previous statements are completed, okay. And you have to remember this one also, that it happens in serial fashion, okay. The second one is non-blocking assignment, and this is the non-blocking assignment, okay. But it executes in parallel. Suppose if I write the same statement, A equal to B, but using non-blocking assignment, A equal to B, then C equal to A, then D equal to C. Here what happens here, I have used here non-blocking assignment, and this executes in parallel. Means all the three lines, all the three statements, the first one, the second one, and the third one, all the three statements are executed parallelly. They do not depend on each other, okay. Here you can see here, they do not depend on each other. Means when at 0 nanosecond or at 0 time step, this line will be executed, then this line will be executed, then this line will be executed. Means the execution of the second line doesn't depend on the first line, and the execution of the third line doesn't depend on the second and first line. That we have to remember, okay? And you should know this, that this is what happens in real hardware. Okay, if you consider real hardware, the circuits are always executed. The circuits are always real. The logics are actually evaluated parallelly and not sequentially. It doesn't wait for some previous data. Okay, so the real hardware implementation is done by the non-blocking assignment. Okay, so if I write a equal to 1b1, b equal to 1b0, always at the rate pause edge of clock, then begin, a equal to b, b equal to a, then end. So what will be the output for this one? Here a equal to 1, b equal to 0. So here as b equal to 0 here, so a will get 0, then b equal to a, because first this one will be, this is a blocking statement, so first this line will be executed. Okay, so a will get 0. Next, after completion of this line, first line, the second line will be executed. Okay, so what will happen? b won't get a 1, b won't get 1, because after this execution a value will be 0, so b will get 0. So a equal to 0 and b equal to 0 after any kind of clock event happens. Okay, if there is a pause edge of clock, if there is a changes in clock, then a will be 0 and b will be 0. But do you think that it is the real hardware implementation? Because here it is written a equal to 1 and here it is written b equal to 0, and a equal to b means this is a buffer, right? A equal to b means simply we are assigning b value to 1, a value. So a equal to 0, it is correct, so there is nothing wrong in it. Then b equal to a, but here a value equal to 1, so b should get 1, but here b is getting 0. How it is possible? It is definitely, it is not a real hardware implementation. So but this is what happens when we use blocking assignment. That's why it is strictly asked not to use blocking assignment in sequential design. This is sequential design, right? Always at the rate pause edge of clock, a equal to b, b equal to, this is blocking assignment we are using, and we normally in sequential design we don't use blocking assignment. Okay, so this is what happens, a equal to 0 and b equal to 0 if I write and implement this code. Okay, the second one is if I write a equal to 1, b equal to 0, always at the rate pause edge of clock, a equal to b, then always at the rate pause b equal to a. So these two block, this always at the rate and always, this is a multiple always in a single piece of single your what you call this logic. Okay, so these two are executed parallelly. Okay, always if there are number of always block, then they are executed parallelly actually. So what will happen here? A equal to b. So, and we don't know which one will be evaluated first. It depends on the simulator whether, because these two blocks always at the rate pause and this always at the rate, this is executed parallelly. So and it depends on the simulator whether this one will be evaluated first or this one will be evaluated first. Okay. So what happens here? A equal to b. If a equal to b, then a equal to a will get 0 if this one will be executed. And what happens here? If b equal to a, then b will get 1, right? Because a equal to 1 and b equal to 1, this one, so b will get 1, right? So if this block will be executed first, always at the rate pause edge of clock, then what we will get? A equal to 0 and b equal to 0, and it will remain there. And if this block is executed first, then we will get b equal to 1 and we will get a equal to 1, and this will remain there. Okay, and there won't be any changing in these values. Okay, once this block will be executed, we will get always this one, a equal to 0, b equal to 0, and if this always pause edge of clock, this block will executed first, then we will get b equal to 1, a equal to 1. Okay, so here it is. So either a equal to b equal to 0 we will get all the time, or either a equal to b equal to 1 we will get all the time, and that value will stay that way and there for any future clock event. Okay, this is what happens if you run this code, this piece of code. Okay, so the next one is a equal to 1, b equal to 0, always at the rate pause edge of clock, begin. So this is also blocking statement, right? This is also blocking one, this one is also blocking, and this one is non-blocking. A equal to 1, b equal to 0, always at the rate pause edge of clock, begin, a equal to b, b equal to a. Okay, this is also read a equal to means for blocking and non-blocking we use equal to, and not like there is nothing, not different way, no different way to read non-blocking assignment, the same way only. Okay, so a equal to b and b equal to an and. So what happens at pause edge of clock, when the first positive edge of clock comes, then what happens? See, a equal to b, so what will happen? Your a will be assigned by the b value. So b, initially b equal to 0, so a will get 0. And because see, non-blocking assignment, it runs parallelly, right? So this code, this line and this line, the first line and second line, this runs parallelly. So at 0.9 nanosecond or at 0 time step, this line will be evaluated and this line will be also evaluated. So at 0 nanosecond, what b will get? What b will get? Because b will be assigned a value. So a equal to 1. See here, a equal to 1. So b will get 1. So at first pause edge, when the first positive edge of clock encounters, we will get a equal to 0 and b equal to 1. Correct? The when second positive edge comes, okay, when second positive edge comes, then what happens? What we will get? A equal to, now b value equal to 1. Now the b value has been changed to 1. So a equal to b. So what we will get here? A equal to b means now the b 1 will be assigned to a. So a equal to 1, right? And then, and what is b value? B equal to a. So a is already equal to 0. Okay, the first clock edge. So b will be 0. This way it will continue. So it is like negating. Every clock the value will be flopped. Okay, so 1 will be 0, 0 will be 1. So see here, first clock 0, then 1, then it will be again a equal to 0, then it will be equal to 1. So this is a continuous negation of data or bit in every clock, when for each clock. Okay, so this is the desired behavior and will match the hardware. Okay, so this in this here I mentioned that this non-blocking assignment are real hardware implementation. So this is what the hardware behaves, the real hardware. How this is the behavior of the real hardware, and not this way, this one. Okay, not this one, but this one. So non-blocking assignment actually it will give you the real hardware. Okay, and the desired behavior it will give, the real hardware behavior it will give, but not the blocking assignment. Okay, in the sense for sequential design. Okay, the next one is a equal to 1, the same one. Okay, the same one we will see again. A equal to 1, b equal to 0, always at the pause edge of clock. So here we use blocking assignment. Now the same statement and we will non-blocking assignment. Okay, then what will be the output? So this is again this always at the rate and this always at the rate, it is executed parallelly. Means we don't know and whether first this block will be executed or this block will be executed. It depends on again simulator. Okay, so when the first pause edge of clock comes, okay, so what will happen? A will get what? A will get old value of 0. And what is old value of 0? Okay, if for example this block is executed first. Okay, so what a will get? B equal to 0. B was 0, so a will get 0. And what b will get? Here what b will get? B will be 0, because initially b equal to 0 here. And what here it will get? Always pause edge of clock. B will get the old value of a. And what is old value of a? Old value of a is old value of a equal to 1, right? It is old value of a equal to 1 and a equal to 1. Okay, so this way it will work. So first, so here simulator can choose because it depends on the simulator whether this block will be executed first or this block will be executed first. Okay, so after first clock, a will get the old value of b and old value of b equal to 0. So a will be 0 and b will get the old value of a, that is 1. And the second clock, what happens? A equal to 1, a equal to 1 and b equal to 0, and they will continue to flop every clock. Okay, see, you can see here next what will happen? A equal to Okay, so after second clock, this A will be 1, A will be 1, and B will be 0. Okay. So again it depends on the simulator actually, because whether simulator is executing this block first or this block first, and but depending on that one, depending on if you implement this code in your simulator, you will get this flopping, means continue to this data will, the bit will continue to flop every clock. Okay, so this is also desired behavior of the real hardware. So it will get like 1 0 1 0 1 0 1 0, like this you will get. Okay, means it is like okay. So this one you have to remember. Okay, this non-blocking assignment for sequential design will give you a hardware, real hardware, but not the blocking assignment. Okay, and this where this blocking assignment has to be used, normally the blocking assignments are used for ideal for combinational logic. Okay, this is normally used for combinational logic, and this blocking assignment means evaluate and update immediately, and this is ideal for combinational logic, and all it is assigned and not the positive edge of clock. Means when we use this blocking assignment, normally it is say this positive edge of clock means a sequential design, because combinational design doesn't depend on the clock, right? So when we write always at the rate star, means it is kind of always at the rate A or B or C kind of thing. So there is no clock, mentioning of clock. Okay, there is no something is not changing with respect to clock. In that case, we can use this blocking assignment inside the always at the rate. Okay, so this is to implement a combinational logic. Just remember that blocking assignments are preferred, or blocking assignment is used normally for to implement a combinational logic. And this non-blocking assignment, what it does, it evaluates immediately. It does evaluate, means the right sides are evaluated, these right sides are evaluated immediately, but it waits and postpones and the update until other planned evaluations in the same time step has been completed. Okay, and normally sequential logics are designed using this non-blocking assignment. Okay, because it gives you the real hardware. Okay, because here we saw that how this behavior, it matches the real hardware. Then in non-blocking assignment, all the statements are evaluated before any left sides are updated. In real-time logic, gates operated independently rather than waiting for this is very, very important. Okay, this line. Okay, so what happens here, for example, always at the rate pause edge of clock, you will understand this line, what does it mean. So Q0 is data in. So in non-blocking assignment, all the statements are evaluated before any left sides are updated. So first all this data in Q0, Q1 and Q2, the value will be assigned to this one. First the means data in will get its value, then Q0 will get its value, then Q1, then Q2. All this value will get their own respective values. Then after assigning, means after having their own value, then these values are assigned to left hand sides. Okay, all these statements are evaluated. This data in Q0, Qn and Q2 are evaluated at 0 nanosecond, because the non-blocking assignments means it is definitely all these are executed parallelly. So first the right hand sides are evaluated, then it is updated to the left sides. Okay, and this is the real time logic gates, right? Because in real time scenario, the logic gates, they operate independently. Okay, it doesn't depend, it doesn't wait for the completion of other gates. Okay, because what it does, it unless and until it gets the new data, it propagates the old data to the output. Here we can see this is shift registers. Okay, so we get, for example, if it is data in equal to 0 and Q0 is, because data in will be assigned at when the there will be a changes in positive edge of clock, then the Q0 will get data in. Let's say 0 equal to 0, I gave a data bit 0 in data in. Okay, so the Q0 will get data in. What about Q0? What Q1 will get? Q1 will get Q0, but what is the data of Q0? Not instantly, because I have given 0, that doesn't mean that the 0 will be propagated to Q0, then that same 0 will be propagated to Q1, then Q2 to Q3. No, it is not transparent. Okay, it is not transparent. So what will happen, the Q1 will get the previous value of Q0, only this 0 part, whatever the value that I assigned to data in, that value will be updated to Q0, but not the Q0 value will be simultaneously will be updated to Q1 and Q2 and Q3. No, if I will give at the first clock, the Q0 will get 0. Okay, but what about the Q1? The Q1 will get the previous value of Q0, whatever the value the Q0 had before, and whatever the value Q1 had before and Q2 had before. So Q1 will get that previous value of Q0, Q2 will get previous value of Q1, then Q3 will get previous value of Q2. And that's why when we are designing a shift register, sequential logic design, what we do normally, we mention Q3 is to 0 equal to 4 with 0 0. Normally we mention. So we are assigning here values, means it is a predefined value, means we try to we try to give some predesigned logic, predefined data to our output, so that it won't be unknown or it won't be a floating value. Okay, so the Q0 will so Q data will, the first clock data in will be propagated to Q0. Okay, when the second clock comes, what happened, the 0 will be propagated to Q1, third clock the 0 will be propagated to Q2, then a fourth clock 0 will be propagated to Q3. That we should remember this one. Okay, but if I write the same code, using this blocking assignment, what happens, only the first at the first edge of clock, Q0 will get 0, means here Q0 will get 0, then Q1 will get 0, Q2 will get 0, and Q3 will get 0. But this should not happen actually. The blocking assignment, so at first edge Q0 will get the same value, so this 0 will be updated to all the output Q1, Q2 and Q3, and this is not the behavior of real hardware actually. Okay, so normally we use non-blocking assignment for sequential design. So the first edge 0 will be assigned to Q0, and the Q1 will get the previous value of Q0, but not the updated value of Q0. Okay, so here it is written, here on each clock edge data should be shifted to first flop, then first flop shifts to second, and so on. Q1 will get Q0, and not value of data in that is loaded into Q0. That is what I explained. Data in won't be updated to Q0, Q1 and Q2 and Q3 at first instant of clock, first edge of clock. It will take four clock pulses to be shifted the data from here to here. Okay, but not only a single clock, but not with the single clock. Okay, and another example is there. Here we can use both blocking and non-blocking assignment. Okay, you should remember this one. Blocking and non-blocking assignment can be used for range. Okay, both blocking and non-blocking. If I write A equal to 1, B equal to A, and C equal to 1, and if I give input as 1, so what will happen? A will get 1, then B, because these are sequential. Okay, these are parallel implementation. This is sequential implementation. So what will happen? The A will get 1, then B will get the same value 1, then C will get the same value 1. So it is a kind of buffer, right? It is a combinational logic, because the C will get what the B got, and the B will get what the A got. Okay, this is a combinational logic. But if I write the same logic using non-blocking assignment, then what will happen? It will be a sequential circuit, and it will involve a real hardware, that is a flip-flop, real hardware. So the first instant, what will happen? The A will be the 1 will be propagated to A, the B will get A value, but here not 1, here B won't be 1, but what B will get then? In this case, B will get the previous value of A, whatever the value A had before. It can be 0 or it can be 1, but not this one, B won't get this one instantly. Okay, and what C will get? A, but not the value of A, not this value, but the previous value of A. Sorry, this one is B. Okay, not this one is not A, this one is B. Okay, so these are previous value. So these values in non-blocking assignment, these sides are evaluated or assigned at 0 nanosecond. Okay, so it will be evaluated, but it will be updated to left, later it will be updated to left side. Okay, so it is a real implementation of hardware, that is a sequential circuit. Here 3 flip-flops, because 3 intermediate data we have to store. A data we have to store, B data we have to store, and C data we have to store. 3 intermediate data. Okay, so 3 previous data we need to store. So we have 3 flip-flops here, 3 flip-flops per 3 previous data to be stored. Okay, so this is how the blocking and non-blocking assignment works. And you should remember that blocking assignment is normally used for hardware combinational logic design, and non-blocking assignments are normally used for this sequential logic design. It is very, very important, because normally while you are designing a digital logic, and often people forget that when to use blocking and when to use non-blocking assignment. And during interview also they will ask you that difference between blocking and non-blocking. They might ask you to implement a logic and what and how this will infer a hardware, real hardware. Okay, so now it is a very, very a little bit long video. Okay, so thank you so much for watching, and if you liked the content, then please press the like button and subscribe this channel. Thank you.